Hi everyone, welcome to the Power Grid Model Workshop. I'm Jen, now working as a power system simulation consultant in Alliander. And next to me is Nitish. So we're going to present some examples of using Power Grid model. So can you introduce yourself, Nitish?
Yes. Hi, I'm Nitish, a scientific software engineer, also part of the Power Grid model team, working here at Alliander. Yeah, we can start. Back to you, Shen.
Yes, so also right here in the room, we also have our colleague Matai, who helped us with the camera and the video recorded, and he works as an external employee. So we are the three person that mainly responsible for today's workshop, and our group is actually holding this event as a promotion about the Power Grid model, and we want to help the new users to get to know the library quickly. So let's go to the agenda. There will be a brief introduction of the Power Grid model, including the model function and the calculation method. And after that, we will give an example of power flow, and also based on different topics, we will have a different assignment, as you can see, 6 of them. So the examples and assignment will go in a parallel way. We will jump back and forward into from examples to assignment. So you can use what you learn from the example and try to do the assignment on your own. So I will mainly responsible for the presentation and the first 4 assignments. And after the coffee break at the 3 o'clock, Nitish will take over and give another assignment, including the error handling, state estimation calculation, short circuit calculation, and the serialization about power grid model. Yeah, so that's it. So I assume that most of you guys already have a basic knowledge about power grid. So we're now starting with the main function of power grid model. And the first one is, of course, the power flow calculation. It is a what-if analysis where you use the network data and the assumed load and generation profile. And you can imagine that with such a grid structure and the input data, what will the status of the grid will be. And and another one is the state estimation, where you use we have the network data and the measurement of power flow in the cable or the line, and we also have the voltage data, where you can estimate the status of the grid. It's more like a estimating algorithm. The third one is about the short circuit calculation based on IEC standard, and where we can simulate the fault with a single impedance, and you can define the location and the type of the faults in the power grid model. So one of the other things we want to mention is actually the calculation method for power flow calculations in PGM. So as you can see here, we have 2 main categories of calculation method, the iterative method and the linear method. For the iterative one is actually iteratively solving the equations and trying to give the exact solution within a given input tolerance. And we actually have 2 ways to solve the equation. The one is the Newton-Raphson. It is, of course, traditional, but quite robust. And the other one is the iterative current. So based on our previous test, it's actually faster than the Newton-Raphson method in certain cases, especially when the grid is quite distributed, and it's using the Jacobi method, which is equivalent to the backward and forward sweep, if you know more about the radio networks. And another category is the linear method, where we are giving some approximate solutions over here. And we're using we can use linear impedance to simulate the load in the grid. And we can also treat the load and generations as a linear current. And the reason why we want to present this solution, approximate solution, is that if we're trying to, let's say, predict the grid in the future 40 years, and the input data is quite big, and we need huge amount of computation, we think using such a fast speed calculation is reasonable, and we are trying to make a trade-off between the accuracies and but we have a shorter computational time over here. Let's go to the Power Grid Model Workshop home folder. And I would like to, we will see there are data examples and the power flow assignment and state estimation assignment. Let's first go to the examples where you can see different calculations where we all set different examples. But today we are more focused on the power flow examples. And here it is. So in this notebook, we will walk through the example of a power flow calculation, and there are a few points are covered. For example, we will talk about how do we build the grid in the power PGM, and we will run the power flow once and introduce its relevant function arguments. And what if there's an update or change in the grid, how to change the model, we will introduce that. And after that, Nitish will help us run some batch calculations and also introduce its relevant function arguments. And we also mentioned about the error handling stuff in the PGM. So to start with, I would like to introduce you a bit about the example network we used. So throughout this whole workshop, we will use this only one network over here. It has 3 nodes and it's connected actually using it in a triangular way by 3 lines over here. You see the node 1, 2, 6 and the line 3, 5, and 8. And node 1 is connected with a source, while node 2 and 6 is connected with a load. So to start use the power grid model, we still need some basic imports, which is the NumPy and pandas. And we use the NumPy to build the NumPy structured array that used in power grid model. And for pandas, we don't really use it in our PGM, but it will help us to further deal with the data smoothly and fast. So for example, we want to print out our results in the screen, we will use the pandas. And we also need some imports from power grid model, which is the load gen type, the calculation method, and the calculation type. It will help us to construct the data that will be used for power flow calculations. And we also have the power grid model. It is where we do the power flow calculations. And we also need the initialize array to help us build the dictionary of input data. So these imports are from power grid model repository. So we first need to build the input data set. And this is actually is finished by using the function initialize the array. And there are actually 3 points we want to mention here. First of all is that for all the different component units, we use the SI unit. For example, when we talk about voltage, we use the volt, not the kilovolt. And also all the attributes for different components, they are all defined in the NumPy structure array type. And the ID for different component is unique all across the grid. So it should be different no matter the components type. And the keys of input data are predefined. So as you can see from the example below, the attributes from different component is rather different. For example, in the node, we only have ID and URated, but for lines, we have different ones like ID from node to node. And for those kind of informations, we refer you to the component link over here. If you click the component, you will open the documentation of power grid model where we have one section called components. You can check all the definition of different components. For example, if we want to know about the input data of the node component, let's check this table. You can understand the URated, the description of the URated and its unit and whether it's required for the calculation. And where is the valid value falls in what range the valid value falls in. So it's always very helpful when we do the power flow calculations. Okay. So after we fill in all the data for different components, we still need to build a dictionary of different component, a dictionary of NumPy structured array. So this is how we finish it using the input data to build the structured the data here. then one thing to address it here that the input data cannot be changed. So it's already written in the PGM model that we should use input data, and also the red characters, we use it to define different components. It also should not be changed, and otherwise PGM model won't identify it. And for the black characters, you can manually name it as your hobby. Yeah.
To confirm this one thing, the variable names can change, of course. Just the keys of this dictionary are to be constant. The node can only be referred as a node. Line can be only referred as a line. But yeah, everything else, it's all right. And the initialize array again should be of input type for input array. Yeah.
Oh yeah, sorry. Please let me. Sorry, I missed one point. So for the initialized array, the function there are three arguments are required. The first one is the input, where we define the different type of data. And for example, we have input, output, and updated data, where we will use it later in nitish part. And the second one is about to define the type of component, where we have node, and here we have lines and etc. different kind of components. And the third one is about the number of the component. Here we see 3, so there are 3 nodes in our power grid. Yeah.
Allow me to add another point over here. So these are NumPy arrays, and everything that goes inside is a NumPy array. Even though we add it as even though we assign a list to this array, it gets casted into a NumPy array and then gets assigned to this. So instead of mentioning it as a list as well, you can directly assign a NumPy array to it. And I think that's done in the first line of this when we try to create this array. At the node ID, you can see that it expects a NumPy array. So it would be much faster instead of converting to list and converting back to NumPy array. Just a performance step here.
Okay. Yeah. So after we build this dictionary, we can print this input set by converting the NumPy array into a Panda frame by using Panda. So as you can see from this screen 6. Yeah. So now is our assignment time. If you go back to the home folder of Power Grid Model Workshop, there's a folder called the Power Flow Assignment, which you can open. There's a one with solutions and one with blank space you need to fill in. So we kindly recommend you to not open the one with solutions, but try to finish the assignment on your own laptop and having the Power Flow example as tips while you're finishing it.
Yeah, it's not an exam that we are trying to conduct over here, but it's nice to try it on your own. Then you would bump into questions, you would get a real feel of the model.
Yeah.
Yeah.
Okay, and here's so the assignment is actually corresponded with the examples we just showed. So there are 6 of them. We will finish them today. And you can see the input data are stored as a CSV file in the data folder. It's not regular we use when we're trying to do power flow calculations that we manually input all the data here. So you can try to load all the data from the data folders related with the node line source and the sim load component. So to start with, we really need to do the preparations as we mentioned before. We need to import those functions that we need for the workshop. And one special part is that we add a timer to this assignment job script, because later on you can just play a bit with different calculation method and see how the big difference with the calculation speed. So here's an example about how to use the timer. One tips is that you really need to run the script from the first one, and otherwise the system will not import all the functions that you need. So here is the first assignment, where we kindly ask you to load all the input data over here. And it's, as mentioned before, it's a CSV data files from the folder data. And as you can see, there are a few to-dos where you need to do is to replace the 3 dot with the different functions that we need. And and here is also one where we want to we want to know the time that we use to build the dictionary. Okay, so considering our previous experience, we would like to give everyone 10 minutes to finish this assignment. And if you have any questions, please share it in the channel or just raise it through microphone. Thank you.
Yeah, to do this assignment, just have to fill the 3 dots and take your time with it. If you bump into any questions, please put it on the chat and let us all solve this assignment together. So in case anyone missed it, we are trying to solve the assignment 1 from the explanation that Shen gave on how to construct the input data. And yeah, let's see if we can finish that by 10 minutes. That was. Yes, all loud.
Okay, so this was my solution. I think the first step was to do this line. So introduce this function with these arguments, correct? So for each component, in this case, node, line, source, symmetric load, for this, he would loop through all of these and he would run this function for all of those, having read the data frame, the corresponding data frame with the data. And here, since we need the size of the number of inputs, correct, for each, for like the number of nodes, number of lines, etc., it's always going to be this shape. And then I checked the CSV files, and the columns correspond to the attributes, so which are these keys. And so for each of these components, you will run through the column names and then assign the input data to this to the values in the column, converting the column to a NumPy array. And
Yes.
yeah, then we just need to run this function.
Perfect. That's right. You got the right answer as well. Thanks for sharing with everyone.
Thank you.
Next one. Let's bounce back to the PowerFlow example now.
Yes. Yeah. So after we build the dictionary of the input data, our Power Grid model actually have a function to validate it. So, but for the efficient reasons, we don't do the validations automatically inside the Power Grid model, but you can still do it manually, because when we do big calculations, it's not really high efficiency. So this validation is realized by using the function called assert valid input data from the Power Grid model .validation. So you can see from the window that there are 2 input arguments are required. The first one is to give the input data to the input data, and the second one is to give the function about which type of calculation we need over here. And it's a really simple task here, so we will combine it with the assignment 3. So here is just before the PowerFlow calculations, we still have one step, which is called the construction. So we are constructing the model. We are constructing our grid inside of Power Grid model, which the constructor is called Power Grid model here. And the system frequency is by default 50 hertz. So here you need the input data as only as the argument to put into the Power Grid model, and the constructor inside of the code will deal with the construction. Yeah, that's quite simple written now. So here's we can jump to the assignment again to finish the second and the third assignment now, where you just simply need to replace the 3 dots to validate the input data and also construct the grid. Yeah,
Yes.
we will give 5 minutes in total.
Yes, 5 minutes seems enough. It's just 2 arguments.
Yes.
And I do see one question though. If we get validation errors, is that normal? Yeah, well, that's what the validation function is for. And actually, then we find that
Yeah.
it's not something is going wrong when we do get validation errors.
Yeah.
Like for example, for example, when we put in something which does not belong there, for example, if you put status as 5 or 6, that's an arbitrary number. You can't have some of a different number for status. So that's why it might give a validation error. So that's a good thing. And to find out what validation errors that you get, if you can post them in the chat, that would be really helpful. If you do follow the assignments, you're not supposed to get the validation error though. The validation function also checks for weird entries. Some of the entries which we have put in the some of the examples which we have given in our documentation. For example, you cannot put in negative voltage as the rated voltage. So such things are really handy to find out if they are going wrong. When you have a bigger data, it's really nice to do the validation.
Then we can jump to the next topic. And just in case anyone doesn't finish this assignment, we will have a coffee break after the assignment 4. So keep your time. So here we finally can do some one-time power flow calculations, where we call the method is the model.calculate power flow over here. And as you can check, there are 4 arguments for this function with a certain default value. For the symmetry, we have the default is true, and they represent the symmetry calculations. And we also have single phase calculations. And the error tolerance is about the convergence criterion of our power flow calculations. It's like how the errors should be limited into a certain value. And the max iteration is set with 20 by default, where we use to stop our calculations. For example, if there's some situation that the error tolerance is really low and the calculation cannot reach it, it will stop when the calculation reach its max iterations. And the last one is about the calculation method, where we mentioned it in the presentations. And you can see it also here in below. We have Newton-Raphson iteration current, and also linear method use the linear and the linear current over here. This is where you can change the input augment and see the computational speed difference. So the output results are actually stored as another dictionary of NumPy structured array called output data over here. Now, and this is how we get the power flow calculation result. So after that, we could also print out the output result by using the Panda data form here, just like this 7 window. And here is the result. And we could also select the component of the component types in the result data set. For example, here in the window 8, after we calculate the power flow, we could also, in the 5th augment, we could select which kind of component we want to use as an output. Here, we just refer it as a node. So as you can see, when we print out the output data, there will only be node components that will be printed. Yeah. And here is the calculation method. We just talked about it. So one simple example is that we use the linear method to do the power flow calculations over here. You can see the calculation method here is equals to the calculation method dot linear over here. So the result is like slightly different with the Newton-Raphson method, which is the default value of the power flow calculation. For example, you can see for the node 2, and its UPU value is 0.965. While for the Newton-Raphson method, it's about 0.962. So we already mentioned that for the linear method, it's only approximation result. So there will be a difference, but we think the difference is kind of acceptable, so we will use it for the long-term prediction about the grid. Okay, so now we can jump to the assignment 4 here. It's very simple. We just want to do the one-time power flow calculations over here, and we want to print some results, and you can take your time.
Yes, try to print the maximum and minimum line loading. How you would do that using NumPy? It's up to you. And yeah, we give 5 minutes for that. And if you're done, you can go grab yourself a coffee or have a break, and then we can be back at 3:15 or 15:15 in just 15 minutes. That's it. Yeah. If you have more doubts on how things are happening over here, do let us know. I can also mention one more thing the about the arguments, I guess. Let me put that. So error tolerance, one thing you have to keep in mind that the error tolerance and max iterations, even if you do specify your own, if you set something unrealistic, that might give you non-convergence error. So that's that. The error tolerance, when we say here, it is actually the tolerance of the error in the it's the error between the two iterations of voltages. So it's not actually the error within the calculation, but it is how the algorithm for Newton-Raphson works, or any other iterative algorithm works. You don't find the exact answer, but answer correct to a certain specific band. All right. Try the assignment 4, and yeah. The solution is not a big one either. So I guess I can just go through it on my PC. I'm showing via the solutions notebook that we have. So I don't spend much time in typing it out. Yes. For assignment 2, we give the 3 dots arguments as the input data, and we mention the calculation type that we are trying to simulate for. That's power flow. And yeah, and this would tell us that we are validating it just fine. We can construct a object of power grid model by giving in the input data. That works as well. Similar way as this was in the example. Similar way as in the example again, we run the calculate power flow method. Yeah, and the arguments that we specify here are then the calculation method, which is Newton-Raphson, or we can just not put anything since it's the default anyway. To find the minimum and maximum loading, we can use the min and max functions, which apply directly to the NumPy arrays, and we find the minimum and maximum. That's of loading of the power flow calculation. Does anyone have a doubt on this? Yeah, I see thumbs up. That's good. Right. Yes, as you can see, the difference between the execution time for Newton-Raphson and power flow and the linear power flow is, I guess, 4 times in this case. It's in So it's in the order of milliseconds in this small calculation, but in bigger simulations, it might be few hours. And at that point, it makes a difference to use different calculation methods. All right. Now that it's 3:15, we can continue with the next assignment and the content related to the assignment, which is which we will go to the power flow example. Yes, pick it up. To pick it up from where we left off, it was at the update model section. So now, what if we wish to change something within the input data that we have specified? Uh, it's really inefficient to create the input data again, load the model, and then run the power flow. Each time we want to make a really minor change, like maybe switching off of line or switching something back on. Then to overcome this, we shall use the dot update function, of the power grid model. And what do we pass inside the dot update function? We shall pass an update array. So it's going to be created in the similar way as we created the input data, just that we put in update as the first argument for initialization of the array. Then the second one, the name of the component, and third one is the number of components we wish to change. Similar way as it was done in the input side. We have to mention which IDs we are changing. That's at the start, and then we have to mention what is the changed value. We are trying to change the power of the load, the active power of the load in this example. We're changing it to 30 megawatt and 15 megawatt. And we are not changing the reactive power, hence we shall leave that as is. So the nans are the default values when we initialize the array. And when it is as NaN, power grid model assumes that we are not trying to update anything. Everything that goes within this update array is written over the base model of the input data for each of the scenarios and now for this single update data set. Similar way, we construct the dictionary with the specific key names. And in similar way, like it was done in input data, we can run a validation function. This time it's valid batch data. And we can pass in both the arguments, input data, update data, and the type of simulation we are trying to do is calculation type. And then we can call this update method. One nice thing to note is that there's also a dot copy method to the power grid model object. If you use the dot copy method, yeah, it's self-explanatory. It creates a copy over there. After doing the update, the things that are stored inside this model too are modified as per the update data. And we can run the power flow again with this single update. We will find different answer than what we found before. Yes. Does anyone have any question on this till now? Put it on the chat. Yes. Shall proceed ahead with the batch calculation. So what I explained till now was on how we can update, uh, how we can add a single update to the existing data within the model. But what if we wish to run many scenarios which contain time series of the loads in different profiles, or if it's in n-1 contingency situation wherein we turn off one line for each of the scenarios and find out what we get for loading and for what's the power flowing through each of the line. For that, we have to run multiple scenarios, which is the batch calculation. And luckily, we can do it within Power Grid model in a really simple way. Uh, Similar way where we created the update data over here in the update model, we create a 2D ND array. So I shall show from an example here. We try to initialize an array, and during initialization, we can mention the type, which is the update component, and here we specify a tuple instead of just a number. So the first value is the number of scenarios or the number of time steps that we are trying to give, and the second is the number of components which we want the time series to be. So this we can assign using using simple NumPy broadcasting for the ID attribute. So basically, when we put 4,7 in double bracket, that gets broadcasted for 10 times. And you can do it either way. You can specify it 10 times or you can broadcast it. And now we are putting a time series profile on this p specified. So again, as you see over here, it's a 2D array from before that was 1D array. So np.linspace creates a profile which we multiply with a specific uh, value. Before we create the same as a dictionary, and then we try to validate it again with the validate batch data, and then we can run the power flow. This time the update data set or the time series applies to the argument of the calculate power flow, and yeah, we can print the result we get from it. As you can see, we're trying to see the line components results, of which we are trying to see the I from, and we have such 2D array, which is actually uh, the 10 scenarios times the 3 lines that we have within our example grid. Yeah. So like you can see, there are this is a 2D array, and if we remove this, it will be a 3D array. If we just try to see, or if we try to see all of the attributes. So this gets pretty wild actually. If we try to increase the number of scenarios, number of components. And for that, I can share some tips on how we can access these batch data sets. So each data set is a dictionary where we have components as the keys. And then the 3D array is actually IDs times batches and times the attributes. So how do we access the first scenario? We select the component of line from the dictionary of output data, and then we select the first batch, which is the zeroth batch, and that gives us the result of the line of zeroth batch. What if we wish to uh, select the zeroth component? Over here, it's the one with the third ID, but we wish to have results from all of the scenarios. Then we can use slicing over here. We specify colon, comma 0, that's the first component, and we wish to have results of I from of all of the scenarios. And here we get I from of all of the scenarios. And many such tricks can be actually implemented over here, and more details on that can be found in the documentation of NumPy for indexing the ND arrays. Be sure to check it out if you wish to do more manipulations on this. Yeah, are there any questions on this? Uh, because after this, we're going to proceed to the fifth assignment to solve a time series power flow. I did miss one thing though, which is independent batch data set, which I shall come to after this assignment. So yeah, I did not skip it. Yes, I can see a question on the chat that yes, can I clarify that statement which is mentioned here? So when we apply a list of lists to a NumPy array, it gets broadcasted, like I said. So this gets actually assigned as 4 comma 7 and then this multiplied by 10 times. On the way that it gets applied is mentioned in the NumPy documentation like Martin just shared, but just to give you an hint on how it works. There are many such different NumPy tricks which you can utilize. Yeah, it's really hard at times. Indeed, it creates a list of lists and that gets broadcasted. We are proceeding to the assignments, the fourth assignment, where yeah, you have to, sorry, the fifth assignment. We just completed the fourth one. Here we can create the load profile. A lot of the creation of load profile work is already done for you because using pandas is not the objective of this workshop. But what basically happens with this whole block of code is that we create a data frame wherein the column names are the IDs of the sim loads that you have found that you have created at the first assignment of load input data. And then each row is like one scenario, and yeah, each entry specifies the active power of that load, and we are going to skip the reactive power over here. So we have just generated the active power load profile. Oh, I see I have not imported anything yet. So let me do that. And I have to, yes, I'll just switch to a different notebook. But yes, for demonstration purposes, of course, I don't check the solutions when I wish to solve the assignment. uh, yeah, as you can see, time series, time steps, these are the IDs. And now you have to use this data frame for creating the for running the time series power flow calculations. As before, you have to fill these three dots at all places and then run calculation for both of the calculation methods, one iterative and one linear method. Yeah, for this, we shall give you 10 minutes. I think that's enough. We shall be back at 3:38. And if you have any questions, you can just drop it on the chat. I missed one thing, not just these runtime series, you have to plot the results as well. That's a good exercise. Uh, you have to plot it, you have to index it to everything before the sixth assignment. Yeah, this part of code was pre-written with how we can generate a load profile. And let me just run it again. Oh,
Assignment 5.
yeah. I should have solved the assignment while everyone else was solving as well. I shall just do that. Uh, so, yeah, Now, how do we put the profile that we created over here, the data frame, as input for the Power Grid model? For that, we initialize the array, and the three arguments that we had to specify. One was that it's an update type of an array. It's a simload component that we are trying to update, and then a tuple with scenarios times the components. And actually, if we use the dot shape attribute, it gives the same output. So this is a tuple of n scenarios. It's a tuple of n scenarios times components. All right. Then how do we assign the IDs? We use the dot columns attributes, and from there we have the dot to numpy method. So we convert the columns as IDs, then we specify the loads as the active power of loads from the data of the data frame, and Q specified 0, which when we mentioned before, assume before that the reactive power is 0. Then we construct the dictionary in the similar way, and then we validate the batch data if everything we have entered is correct or not. That's using this assert valid batch data function. Let's say if we have some string over here, I guess that would then trigger this function. One thing to note here is that at times when this data to validate is bigger, the time that it will take to validate is far larger, because we do not expect the users to run this validation function each and every time. One of the major advantages of Power Grid model is its performance, and yeah, you would not see the best performance available with the validation function. So you're advised to just run it once and not each time that you run the calculation. So for starters, it's good enough. We have some execution time mentioned. We run the power flow using the similar way that was mentioned before. Calculation method and the update data is mentioned. Then we run the same using a different calculation method, the linear one, for example. And the same thing that was specified during the single power flow run. The linear method is faster, but the results are like an approximation of the correct results. And then since we did find some output data, we wish to plot it as well to make sense out of it. And to plot it, we can use matplotlib. And here we try to plot the loading. The three dots over here were of how do we select the line loading with ID 2007. So we use the numpy.where function, and then we assign the condition where the ID is 2007, and that's how we find the index. Then we use that index for finding which array it is. And we can use the dot plot, and here we can plot the loading of line with 2007 ID. The result won't really make that much sense because we have generated a random profile anyway. So it's all right if it looks this way. It's not the real grid. Then how do we index something? How do we find the result of some specific component at some satisfying some specific condition? One of the common things that we do after running a power flow calculation is find out where the loading is exceeding more than what we expected, and that's at that's with a condition. And here you can see again we used numpy np.where function. Wherever loading goes above 0.9, we wish to know the time steps. that was asked. So if we get the dot index attribute and then apply the condition, we get the timestamps where we violate this condition. Any questions? I see not. I hope everyone is following. You can definitely ask any question which might be small or big as well that you encountered during solving this assignment. Because I understand that starting from fifth and sixth assignments, it gets a bit more deeper into NumPy. Yeah, uh, we can go ahead with the other way we can run batch scenarios. So till now we ran the time series scenario. Now, if we wish to run the n-1 scenario, it's the same as it was done before for time series. This time we turn off the lines. So in case anyone does not know, n-1 scenario or the contingency analysis is a special situation where we turn off each of the lines of the grid for each of the scenarios and find out the worst possible case among all of them where the grid fails. And yes, here we try to initialize the array in the same way we did for time series. We have three scenarios where we turn off each of the line, and there are three lines. We specify the ID in the similar way that was for time series. And now, instead of modifying something else, we modify the status of the line. The first line is turned off for the first scenario, second for the second, and third for the third scenario. Similar way, we create a dictionary from it, and then we validate the batch data. We run the power flow, and we get some output. As you can see, the ifrom is 0 for the respective lines which are turned off. And now I'll go back to the one section that I did put for skip for a while. That was the independent batch data set. So you can either specify the time series mutation in this way, where you specify everything that changes. All of the attributes, if they are changed, if they are not changed, you specify everything. That's one way to go about declaring the update data. Or you can just mention uh, the things that you are changing within the data set. So here we try to do just that. The same example. We have line and we have three scenarios, and each scenario we change only one object, and those objects are the third line, the line with ID 3 at the first scenario, next with 5, next with 8. Because when we declare the input data, the statuses were already 1. So we do not have to specify it again. We can do it this way as well, and we shall get correct results too. We can again create a dictionary, validate the batch data, same thing again, run the power flow. You'll find the exact same results. The difference between these two methods is that it's recommended for you to assign the uh, assign the parameters that are changing for n-1 scenario, but for time series simulation, you can specify everything that changes. So in the time series scenario, we call it an independent batch data set where we provide everything that changes. And over here, when we only specify everything that changes or not changes, and over here, we only specify the things that change. Uh, each have their own different performance effects, and those are then presented in the performance guide, which Martin will share in the chat now. But that was what was mentioned over here in independent batch data set. For time series scenarios, you provide everything that changes or not changes. But for contingency, you only provide the things that change. Now, if we go to the second topic, that's the caching of topology. So with the independent batch data sets, the reason we do this is because Power Grid model already pre-calculates a lot of things before we run this method, calculate power flow. It arranges all of the matrices in the way that it finds is more efficient. It builds the topology and then arranges everything so that it can calculate efficiently. So if it's, for example, a time series scenario simulation, we don't have to rebuild the topology again and again for each situation, because we will only be changing, let's say, the load or the generation that happens through each of the time steps. For contingency analysis, however, we do change the topology. And the difference between these both situations is that wherever there's a topology change, the uh, building of building of initialization happens again, and then that scenario is then slightly less. Yeah, it's slightly slower than what uh, than without than with caching the topology. So we have mentioned all of this in our performance guide on how you can maximize it for performance. For example, I would select the contingency as the uh, outer outer iteration of the scenarios, whereas the time series as the inner one. So all of that you can find in performance guide. And Power Grid model can uh, also supports parallel computing. It's really efficient at that. You can use different threading options. So threading is an argument in the calculate power flow. We have three options. You can either do the sequential computing, don't use this feature at all, or you can use the threads which are recommended by the hardware, that's with zero, or you can specify any of the threads manually if you wish to. And everything else for parallel computing will be handled internally. Now is the time to go to the uh, fifth, the sixth assignment, which is the n-1 scenario of batch calculation. Yes, you have to fill the same three dots that you have filled till now, uh, and run the power flow. You have to run it for the n-1 situation now. In this case, you have to disconnect one line for each of the scenarios. And then in the next section, you have to use different threading for running the power flow. And then you'll find out what the difference between each run is for when you use parallel computing versus sequential computing. If you find any questions on this, let us know. And for this, we shall give you uh, 20 minutes actually. In this assignment, we intended to do the n-1 scenario calculation, batch calculation. We initialize the array again for this contingency data set in the same way as it was for time series. We specify the first argument as update, the component that we're trying to change. Since there are number of lines are the contingencies, it would be a square type of a data set over here. Number of lines times number of lines. Uh, to then we shall use the same IDs from the input data set to apply to the update data set. And for assigning the from status and to status, we used a trick while using the np.i function from NumPy. So what this function does is that it creates an identity matrix. And then when we subtract one from it, we get the pattern that we see over here when the when the n minus one's scenario of the example was explained. So this is 1 minus identity matrix, and then we get the from status. Or if you generated it in some different way, that's fine too. Same for to status. We create an update data set, which is a dictionary of that ND array. We can assert this. We can validate this batch data set in the similar way as before, and then run the power flow calculation. And yeah, we can run it with both the methods. As you can see again, the Newton-Raphson takes 11 seconds, while this one takes 3. If we do a really huge simulation, it's the difference between 3 hours and 10 hours. So that's you'll be saving a lot of money on your on the place where you're trying to run this simulation. A lot of money and a lot of energy.
We have a problem here. Oh, sorry. Yeah. How would you solve this using the n-y scenario where only the changed objects are specified?
Nice question. So we have it in the chat. How do we solve it? Where we only specify the things that are changed. Not in this way, where we create an independent data set, but in a non-independent one, where where we only specify the things that are changed. That's quite interesting, actually. It's a it's a Python exercise. I may not do it completely right now, but yeah, I shall try. We can make this into a list of lists where each of the IDs are specified for each one of the lists, and I can make this as 0, comma 0 into number of lines, and the same goes for the to status. And I think that's maybe that might be the way you can do it. I might be wrong somewhere here, or I guess this number of lines might go inside. But yeah, a similar trick might be applicable to do this. But let's see if Martin can answer this in the chat, because I guess it's let's not take up everyone's time on that. But yes, it is indeed possible to do it without the independent batch data set. All right. If there are any more questions. Okay, I see some way mentioned in the chat too. That's a great job over there. Yeah. Nice. It's nice to see good participation with different methods being used. I see fill diagonal being used. Interesting. All right. Then we can move to the remaining part of the session. So I think till this point we have covered a lot of the basics of how we can do the simulation, and from this point on, whether you do other different types of simulations like short circuit or state estimation, the whole process is gonna remain just the same. So the miscellaneous topics that we'll cover now include error handling, other types of calculation, and how you can transmit this data to different places that you'll use it. That we shall do using the serialization feature that we have within the Power Grid model. Let's start with error handling. So different types of error can be generated, which you'll come across, and we shall go through them one by one. We shall use the try except blocks of Python to catch any error, and then we can try to print them. So for generating this error, we are going to create some data which does not make sense and then try to instantiate the model. So we created some input data, and then we try to create the instance of Power Grid model. And since it's incorrect, it generates an error, which we try to print here. And it says that for one line with ID 3, we have different voltages at the starting node and the ending node. So this means that the rated voltage at the from node and to node are different. And yes, it is indeed different. One is 10.5, one is 150 kilovolts. So as you can see in the documentation where it's mentioned that a line always connects to the same rated voltage nodes. And we cannot assign it to a different rated voltage nodes. And yeah, that's how cables are basically connected. You cannot connect a cable from a lower voltage to a higher voltage. Transformers, that's all right, not for lines. So that's one type of error that you find. One error that you can also find is that something called ID cannot be found. So when you're trying to update a nonsensical ID, for example, 12345, that does not exist, then you'll get ID not found. And that's possible when you are trying to use the dot update method, or when you're trying to calculate any power flow or state estimation or anything. And there can also be error in calculation where the algorithm failed to find any answers. And for example, we try to calculate power flow here, uh, where we specify certain parameters, and then it gives us iteration failed to converge after 20 iterations. It's a trick question, but if you can identify what goes wrong over here, it's means you really grasped it all about the power flow calculations. Uh, it says that 20 iterations are not enough. Why is that so? Because we changed the error tolerance that we mentioned over here. Its default value is, let's say, 10 to the power minus 8. If we give it as 10 to power minus 20, and that's too short of a band to find within 20 iterations, if it's even possible within 20 iterations. So yeah, a small note as well. If you're uh, really acquainted with power flows, then you can change these parameters by yourself. Hence, it failed to converge and it gave this error. Now, this was for a single scenario of power flow simulation. Errors can occur within batches as well. For example, over here, we try to simulate, let's say the third ID has some, the third sim load has some unknown ID. Then, yeah. And then in seventh sim load, we are giving some really unknown power. It's one e power 100, which is really large, and that would fail the algorithm. So what would the errors be in this case? So we are trying to run a batch simulation. So we use the dot calculate power flow method in the way that we did before. And when we when the try catch finds an error, we go to the except one where we print what the error is. And within the error, there are many attributes as well. The failed scenarios, which scenarios succeeded, what are the error messages for each of the failed scenarios. Yeah, we can print those attributes if we wish to. As you can see in this case, the third scenario and the seventh scenario failed because we gave some data which does not make sense. And of course, the third message is that the ID cannot be found, and the second is that the iteration failed to converge because the power is really large. In this way, you can catch errors on a single scenario basis for a batch calculation. Now, yeah, let's say we are running a simulation over here, you can see that the try block caught an error and we went to an except block. But what if we don't want to end the program or end the simulation over here? Then for that, we use the continue on batch error argument, set it as true. That's at the calculate power flow method. And if we set it true, the calculation will run for all of the scenarios, irrespective of it catches the error or not. And uh, when and we will get some legible results at the output data. And yeah, the results for the scenarios that are failed, we will get some garbage values. So for example, we try to run with the continue batch error equals true. We print the batch error. We at first print all of the results that we found, including the succeeded as well as the failed scenarios. And second, we only print with the succeeded scenarios. This we can do by indexing it in this way. The ones that did fail, though, if we do not, if we print everything, they give out some garbage values. It's zero over here, but it can be any value that you can think of, some e minus 320 or something, whatever uh, is present. So it's always recommended to catch this error and only use the scenarios that have succeeded, or yeah, succeeded, or be wary of what scenarios are failing. With this, we have uh, finished up with most of the basic functionalities of Power Grid model. What remains is the state estimation calculation and the short circuit calculation and the serialization feature. So we don't have a lot of differences between the state estimation actually. If you have followed everything here till now just fine, then you'll realize that the same thing is for state estimation as well. For an example, I'll just go through the state estimation example, by the way. We can run the same, this is the same grid that we covered till now in the power flow example. We import few things, we create an update input data set. One additional thing though over here is that we add the sensors. We add it in the input data set, input, it's sim voltage sensor, sim power sensor, and yeah, what's the measured value, what's the sigma of the measurement, what's the variance. We create the input data in the similar way, just that we have sensors also included in this situation, and then we can validate it as well with the assert valid data. We specify a different calculation type here, and everything that you've seen for power flow is the same as that's for state estimation, and vice versa. You construct the power grid model object, and then you run the state estimation with this function. Before it was calculate power flow, now it's calculate state estimation. And everything else remains the same. How you access the attributes, how you create the whole batch calculation set, everything remains the same. So after we run the state estimation as well, we shall find some results, node, line, sim load, in similar way as power flow. One thing to note in state estimation is that sometimes you might get with another error called sparse matrix error, and that usually comes in when you don't provide enough measurements for the grid that you're trying to estimate. So as a really rough calculation, you can realize that you at least need more measurements than the number of unknown variables that are present. It also depends on where these sensors are located, by the way. But this is a really rough way to calculate if you have enough measurements or not. The location matters as well. And if you ever bump into a sparse matrix error while trying to solve a state estimation, you can be sure that it's where you don't have enough measurements in the grid. This term within electrical engineering is called, or control engineering is called observability of the matrix. And that's something that you can figure out. Now, similar way is for short circuit as well. We do the same imports. We can construct the input data in the similar way as state estimation and power flow. We have, and over here we can specially declare the fault object. Just like we had simload, simgen, and everything else, now we have fault object. What type of fault it is, where does it belong? We can add it to our input data. Then we can run the validation. We can construct the model similar way as before, and then we can run this method, calculate short circuit, to calculate the short circuit current. The short circuit calculation is done using the IEC 60909 standard. It's how most of the softwares and most of the requirement really ask to calculate. There's nothing new there. And then you can print the results as well. In the similar way that we generated all these calculations, uh, these were the symmetrical calculations or the single phase by default. If you wish to generate asymmetrical calculations, uh, you can specify this argument over here. I'm scrolling too fast actually. It's in the calculate power flow argument. Symmetric equals true. Same thing is available for symmetric equals. You can make it as symmetric equals false for calculate state estimation, calculate short circuit. Calculate short circuit does not have a symmetric one, but yeah, you'll uh, get the difference that's mentioned there. So that's how you generate symmetrical versus asymmetrical calculation. That covers most of the uh, calculation methods there. Now, in real life situations, in practical situations, we also transfer the data from one form to other form. Uh, Here I go. One way we can do it is using the serialization that's available as an utility within Power Grid model. Uh, the whole example for serialization is in this serialization example notebook, where you can serialize the data, or you can also have a look at the make test dataset notebook, where you create a JSON file for serialization. To explain what it means is that now that you have created something like this, input data, you wish to save it somewhere, you wish to share it with someone, or maybe you have another application before Power Grid model, or you have another application after Power Grid model. And it becomes nicer to either export it to a different form if this passing is being happening. Of course, you can directly pass the numpy arrays if that's possible. That's the best way. But if you wish to, let's say, export to JSON, you can use the JSON serialized to file. To export it to JSON, you can give a path to it and the things that you want to export, and then it creates a file with these attributes to its values. This you can do with JSON. You can also import it. The JSON format is slightly less efficient at storage, but it's nicer to view things in JSON format, and hence to have a really efficient way of transmitting, you can also use the message pack library. Just as JSON serialize and JSON to serialize, you have message pack serialize and message pack to deserialize as well. Those files are a lot less in size than JSON one. All of these are covered in the serialization library. Does anyone have a question about this? Um, yes, I don't see any questions in the chat as well. But yeah, that does cover it all. there are such different different utilities within Power Grid model and around Power Grid model as well. Again, one of which I did not cover was the PGM IO repository. That is to convert the Power Grid model data from Power Grid, like from or to Power Grid models to different types uh, of storage of the Power Grid data. It can be right now, for example, we can convert the Panda Power net and Vision net from those files to the PGM format of NumPy arrays. Those will also be mentioned in the chat on how you can go around it. There has been a lot of content, and
Yes.
I'm really thankful to everyone to have stuck with us for so long. Thanks to all for joining. It's been really nice. Great participation from everyone. Good job in solving the assignments. Okay. Thanks all. Stop sharing too. Because there are more ways to remain connected with the Power Grid model community. We shall share a lot of information from the LF Energy channel. We've been doing that now and we'll do that more.
So it's
All
time
right.
to say goodbye.
Thanks.
Yes.
Bye-bye.
Have fun with Power Grid model, and hopefully everything goes smooth. We will see you in the Power Grid model meetup.
Yeah, hope you develop a hobby of running power flow simulations.
Okay.
Nice.
Bye bye, guys.
Bye-bye.